let's talk about the chain rule. Now, before we get started, I want to remind you that we know how to find the derivative of a constant times a function. We know how to find the derivative of a sum of two functions, and we know how to find the derivative of the difference of two functions. We know how to find the derivative of the product of two functions, and we know how to find the derivative of a quotient of two functions. So what we want to talk about today is we want to talk about how do you find the derivative of a composition of two functions, okay? So we're going to let f and g be functions, and for all the x in the domain of g for which g is differentiable at x, and f is differentiable at the output g of x, the derivative of the composite function h of x is going to be equal to what? Well, first let's describe what this composite function is. The way we write the composition of two functions is we write it like this. We write it as f composed with g of x. And what that means is you're first going to take your x value, you're going to plug it into g, then you're going to take the output of that, and you're going to plug that into the input for f. Okay, so that's what a composition of functions looks like. Now, I was thinking I would draw a little machine diagram to help you visualize what I'm talking about. So I want you to imagine your x value is here, then you plug it into this machine, and this machine is called G, and then the output, when you plug it in, is G of x. Then you plug that result into a new machine called F, okay? And when you look at the output of that, the output of that guy is going to be f of g of x. Okay, so this is what a composition of two functions means. And this machine diagram is probably a good way for you to think about it. Now, what we want to do is we want to find the derivative of this composition of two functions. And the way that we're going to find the derivative is as follows. There's a formula. It's a big deal. It's probably my favorite differentiation rule. And this is how it's going to look. We're going to take the derivative of the outside function. We're going to keep the inside function, and then we're going to multiply by the derivative of the inside function. So I'm going to even write that out in words. Okay, you take derivative of the outside function. We keep the inside function. And then we're going to multiply by the derivative of the inside function. All right, so let me highlight this formula because it's for sure a big deal. We use this all the time in calculus. Okay, great. So this formula that we've just written here, this is what I call functional notation. Functional notation. Okay. And what I want to do is I really want to look at the chain rule using Leibniz notation as well. There are certain advantages to using Leibniz notation. It makes certain ideas a little bit clearer. So let's write down the chain rule using Leibniz notation. So alternatively, if y is a function of u and u is a function of x, then when we calculate the derivative of y with respect to x, it's going to look like this. It's going to be dy du times du dx. Okay? So when you look at this, you could see that it's going to be two things multiplied together, just like this function notation had two things multiplied together. We're going to take the derivative of the dependent variable y with respect to an intermediate variable u. So that intermediate variable u you can think of u as the g of x. So this u is really, this is g of x. Okay, we're basically treating that inside function as a variable. And so we take the derivative of the dependent variable y with respect to this intermediate variable u, which is g of x, and then we're going to multiply by the derivative of the intermediate variable u with respect to x. But since u is really g of x, that's really like saying multiply by the derivative of g. So these two equations are really saying the same thing. So I'm going to highlight this equation as well. I mean, they're both the chain rule. And I am going to just remind you that this is Leibniz notation. All right, why don't we take a look at an example? So if we look at example one says, find the derivative of h of x. That's the composition of two functions where it's 1 over 4x cubed plus 1 squared. So I need to see a function inside of a function. All right. So the first thing I'm going to do is I'm going to take h of x and I'm going to rewrite it in exponential form. So when I rewrite this guy in exponential form, this guy becomes quantity 4x cubed plus 1 to the negative 2 power. We have a negative exponent here because this expression is in the denominator. And when I write it like this, I hope that you can see what the inside function is and what the outside function is. So for this example, let me just write it out explicitly. The inside function is going to be equal to 4x cubed plus 1, and the outside function is going to be x to the negative 2. All right. So now let's take the derivative h prime of x. So I'm going to take the derivative of the outside function. That's going to be negative 2 times quantity. I'm going to leave that there. I'm going to put a negative 3 because I'm using the power rule, right? So I have to bring down the exponent like I did here, and then subtract 1 from the exponent like I did here. Then the next thing we said we want to do is we want to keep the inside. When I say keep the inside, I mean just plug the inside function back in. So then this is going to be a 4x cubed plus 1 on the inside, like that. And then I'm going to write an extra step. I'm going to put times the derivative of the inside function. And the inside function is going to be 4x cubed plus 1. So I'm going to break this example up into two steps. I think it's not a bad idea because sometimes you'll have like double or triple chain rules and it's easy to confuse yourself. So it's good to like take things step by step. Okay. So I'm going to copy what I had before, which is negative 2 quantity 4x cubed plus 1 to the negative 3 power. And then now I'm going to multiply by the derivative of the inside function, which was 4x cubed plus 1. So to do that, I'm going to use the constant multiple rule and the power rule. So according to the constant multiple rule, the 4 just stays there. And then according to the power rule, I'm going to multiply by, I'm going to bring the power down, so the 3 comes down, and then subtract 1 from the exponent. So that's going to be a 2 there. And the derivative of 1 is going to be 0. right? So what I can do now is I can simplify my answer. Um, when I multiply -2 times 4 times 3, that's going to give me -24. Let me put the x squared in front, and then I'm going to have 4x cubed plus 1 to the -3 power. And that's my answer. All right, everybody. We'll work on a zillion examples in class together. Take care.